starts to become quite simple because there's only a bunch of classes of patterns. There's like thousands of patterns, but in the end, only a few of them really matter. Guard patterns are one thing, iteration patterns are the other thing, some input-output patterns, this initialization pattern, but in the end, there's not too many, and it's easy to, after 1 year, you will know or notice most of them. Okay, and in the end, you have to combine them, of course. So what do you do?
Question.
Oh, yeah.
The question is, where the address of the pointer is stored?
Sorry, I didn't catch that.
Oh, the address of the pointer. Where is it stored?
The address of, oh, that's interesting because there's two things that you could mean by address. Address of the pointer could mean where is this variable stored in memory, and where is this variable pointing to in memory. There are two different things. If you say the address of the pointer that's usually where is this variable stored in memory. But I think you're actually referring to how does this know where it's pointing to, right?
Yeah, exactly.
I mean, there's multiple sources where you can get that. For example, what you can do is, there's a function called str_dub, which basically duplicates a string and gives you back a pointer that you can put inside of your p pointer or s pointer, whatever you want to call it. This would just give you magically an address. You don't know where exactly it is, but you can be sure that this is a valid string. Or sometimes str_dub returns null if there's if the memory is already completely used. str_dub might fail. So if you look into the documentation, it will tell you it's either going to return null or it's going to return a valid s, which also is a pretty good use case of this pattern. So you just put it in between just to check if it actually returned null or not. But your question was like, where does this point to, or what exactly is your question? Like, where you get? Yeah.
Like pointer s, okay,
Mhm.
it has an address value like 118.
Yeah.
But that number, where is it stored?
This is stored on a memory space called the stack. I didn't want to get too much into it, but technically speaking, when you write code, there's two pieces of memory where you can store your data. Now I need a bit more space again. I think I'm going to fresh space, awesome. So yeah, you usually have two big memory locations. The first of, one of them is called the heap, and one of them is called the stack. And as you can see, I'm drawing them a bit differently because they also differ in functionality. The heap is basically random access. So both of them are actually random access, but in the heap you can malloc. Every time you call malloc, it will reserve a block in the heap. Every time you call free, it will remove it out of here. So the heap is something you can freely talk to, and let's say I want a kilobyte of data from in here, it will happily give it to you. And in here, it will give you another block if you allocate more, and maybe this, and maybe that, and then you want to free this one again. So this is what you can do in the heap. The heap can also grow. So whenever you see a program taking up gigabytes of memory, like Google Chrome for example, or some kind of game engine, you might have experienced that, then it's mostly the heap that's actually overflowing. So the heap is going to go bigger and bigger. It can grow almost indefinitely. Even virtual memory is allowed, so it's more than 8 gigabytes. It can be as big as you want. Of course, the machine will at some point stop you because the RAM just isn't enough, and the disk also, but in the end the heap is virtually unlimited, and you can access it freely using malloc, or free, or whatever you want, like str_dub for example, or you can even write your own functions if you're interested. Again, experiment. This is the important stuff. The stack, however, only grows upwards and downwards. So it's like a glass of water. Speaking of which, yeah, it's like a glass of water that you can fill, or some kind of, a stack of items that you put on each other, like a stack of cards maybe. And for example, this stack grows whenever you do a function call. So when you do f and maybe g, some kind of functions that you call, the space, like when you write a function like f, and it returns something, and you say int x in here. This x will be stored inside of the so-called stack frame of this function. So this will just grow upwards, and for example, this one is 4 bytes often. Ints are often 4 bytes, so what this will do is it will put 4 bytes here onto the stack, and these 4 bytes are going to be used as the variable x. If you also have int y, what it will often do is it will also put a y variable here. You don't know in what order they are, but they are definitely inside of the stack frame. And now if you call the function z, for example, you put it right at the top here, and if this function returns, this memory will just be filled. So you basically have a pointer, actually a pointer, which is inside of your CPU, inside of the machine, that tells you how full this class is, or how high the stack is. And once you have, once the stack is full, of course, you cannot go over the limit, in most cases. And once you return from a function, the stack grows smaller again, and there's space again for more functions. So if you write a function that's z, which just calls z again, what is this going to do? It will call z, which will call z, which will call z. So it will just put things on top of each other, and at some point you're going to crash because the memory isn't enough. This is also this is a stack overflow, as it's called. So if you go if you go through the ceiling, if you blast through the ceiling and have some kind of nuclear cloud here, if you blast through the ceiling, this is a stack overflow. This is a pretty long answer, but I think you're seeing where the pointer addresses are getting from. So what you can say, for example, is if you have an int pointer, so it's an int star, which is the pointer, and you can say, okay, I want this will also be put on top of here. So pointers are often 8 bytes, so it will take 8 bytes for the pointer p. And if you say p points to x, this is how you'd write it. You don't say p equals x, because then it will just copy the bits from here to there. But you don't want to copy, you want to reference these bits so that you can, you have some kind of number location in here, and you don't want to take this out and copy it into your pointer, because oftentimes you don't know what your pointer should point to, because these numbers are so random that you don't know what to point to. But if you want to point to the variable, what you do is you write the ampersand in front of it, and then it will give you its address. It will give you this number in memory, where exactly x is located. So if this is technically not 0, but let's put a 0 here and put some kind of max number in here. And let's say x is stored at location 42. What else? And then y, this is 4 bytes, so y will be at 46. And again, 4 bytes, so p will be at 50, most likely. What's going to happen is, if I just said, put x in here, and maybe x is equal to 5, what is this going to do? Well, 5 is the bit pattern 0, 0, 0, 0, 0, 1, 0, yeah, 1. This is basically the number 5. So what this is going to do is it will, if you say p equals x, it is just going to put this bit pattern into p. And since it's now putting 5 into p, p is now pointing to number 5, to some memory location that you didn't intend to make it point to. So this is not what you want, because now you're accessing some point of memory. Could even be, if this is not 0, but maybe 20, if you're accessing memory location number 5, this is actually the dangerous space, and you're just going to crash whenever you try to access p. Not good. So what do? You put the address here. And now the system will go find the address of x, which is 42. The system knows that. So it puts 42 inside of your pointer, and now your pointer is not pointing towards some dangerous location, but it actually is pointing towards that. Again, the arrows that I'm drawing here is just our interpretation of the numbers inside of the CPU. The CPU doesn't care. We're the ones who are going to keep these things straight, and the most convenient way is to write a pointer from p going towards x.
But when is, obviously this would just be a compiler error, but when is there a time where the compiler thinks that it's okay, but it still puts something in?
That's funny because C will oftentimes not stop you from doing stupid things. So what you can do is say P equals char pointer 42. You can do that and the compiler won't complain. And if you do this, you're basically the one who is in charge. You can tell the compiler, don't care about your internal warnings, I really mean this, and if you do this, the number 42 will be put into P. This is actually how null works. Null, oh my god, so null, this is an N by the way, null is technically, this is actually true, null is implemented as void pointer 0 on most systems. No guarantee, but on Mac and on Linux, this is really true. So, and this is why it's so important when you say, okay, if P equals 0, many people do that, or they might also do P or if not P, which basically means exactly the same as this, then you're basically thinking or assuming that this is how null works, which is not always the case. Sometimes I've really seen implementations where this is the case, and then this would fail. But this is only a side issue. If you really want to trick the compiler into interpreting numbers as pointers, by the way, this void doesn't really have anything to say. Void pointers basically means a pointer to something that I haven't specified. It doesn't know the size of it, so char pointers have exactly one byte in its size, but void pointers, the system doesn't know, it only knows it's a pointer. If you give it an int pointer, it will point to 4 bytes. If you give it a pointer, this is technically a pointer to something, so in the end, you're pointing to a block of bits that's 8 bytes large. So as you can see, things can get confusing with this, and therefore it's important to really know the rules behind that. You can Google them, of course, but I might also do a short talk on how this works exactly. Technically speaking, it's a pointer. You can force numbers to be pointers, you can force pointers to be numbers. Forcing pointers to be numbers is also part of the ftprintf, so this is already a spoiler alert here. Right, so you can convert anything into everything else. And when you go into the memory here, it might be the best solution to just do something like this and be happy with that and not fumble around with the direct numbers, because you're going to shoot yourself in the foot if you do this. Right, so one other thing, this stack is sometimes dangerous. If you keep a pointer to a variable that's on the stack, and if you return from the function, let's say function z and function g both return, function z won't, by the way, because it's recursive. Yeah, let's just fix that. Z returns, g returns. This space is now free. But technically, if we have a pointer going here, this pointer doesn't go away. It's still a bit pattern, the computer will still reference this block of memory. The only problem is the function has returned, and therefore this block of memory is not valid anymore, which can happen. And yeah, if that happens, you're probably going to get no error at all at some point, because the data that's in here hasn't changed, probably. This pointer just went down, telling that the stack is now lower, and this data is just garbage, but the garbage still remains unchanged. The system just doesn't delete this, it just leaves it as it is. Maybe the next function call will overwrite this data, but as long as this doesn't happen, this data can or might still be valid. So there might be mistakes or bugs where your code crashes sometimes and sometimes not. So this is another point for your error sheet that you hopefully are making at some point, that if you keep a pointer to a stack variable, it might just have been thrown away by the system. And this is why some memory locations suddenly change. If you do a pointer into this, and if you free this block of data, the same thing will happen. Some malloc might again reserve this data block, and then two pointers are pointing to the same data, assuming that they're both valid, while they are not. So as you can see, memory can be a pretty tricky issue, and also something to pay attention to. But in the end, it's all just bit patterns. And this is I think, in my opinion, the calming part about this, because if you know the bit patterns, you can most likely figure out what went wrong. If you don't look at the bit patterns, things are going to be difficult at some point. But there's still people to ask, so we have a community. Okay, anything else at this point? So I think we are slowly running out of time, so what I'm going to do now is maybe take a few questions and do the rest in another lecture, if that's okay. I hope you're all settled for at least a bit of C programming. I'm sorry that I didn't introduce you to most of the language features here, but this is basically also a lecture on its own and without the foundation. Learning just C and how it works is pretty useless without the mindset. So I hope you got something out of it. If you have any further questions, make sure to message me, and you can also talk to me if you see me. And yeah, thanks for being here, and see you around. Thank you.